chemical bonding introductions. 5.1. Why our atoms are held together in chemical compound? There must be some force that holds them together. You have already learned in lower classes that the force holding atom together in a compound are the chemical bond. How are chemical bonds formed between the two atoms? There are two-way formation of chemical bond. First, by loss and gain of electrons. Second, by sharing a pair of electrons between the two atoms. In either process of formation of chemical bond, each atom attains a stable noble gas electronic configurations, which electrons are involved in the formation of chemical bonds. The electrons present in the outermost shell of an atom are involved in the formation of a chemical bond. Causal and Lewis approach to chemical bonding. Number of attempts were made to explain the formation of chemical bond in terms of electron, but the first satisfactory explanation was given by W. Causals and G. N. Lewis independently. They gave a logical explanation of valence, which was based on the inertness of noble gases. On the basis of this, they proposed a theory of valence known as electronic theory of valence in 1916. According to Lewis, the atom can be pictured in terms of a positively charged kernel, the nucleus plus inner electrons and outer shells that can accommodate a maximum of 8 electrons. This octet of electrons represents a stable electronic arrangement. Lewis stated that each atoms achieve stable octet during the formation of a chemical bond. In case of sodium and chlorine, this can be achieved by transfer of one electron from sodium to chlorine. Thus, Na plus 2,8 and Cl minus 2,8,8 ions are formed which held together. In case of other molecules like hydrogen, fluorine, chlorine, hydrochloride, etc., the bond is formed by sharing of a pair of electrons between the two atoms. In this process, each atom attains a stable outer octet of electrons. Octet rule. In 1916, Coulson and Lewis proposed an important theory for explaining the formation of chemical bond known as electronic theory of valence. This theory is mainly based on octet rules developed by Lewis. Octet rule is based on stability of noble gases due to presence of 8 electrons Ns2 Np6 in the valence shells. This rule that this rule states that during the formation of chemical bond, atom loses, gains or shares electrons so that its outermost orbit valence shells contain 8 electrons. Therefore, the atom attains the nearest inert gases electronic configurations. The octet rule is found to be very useful in explaining the normal valence of element and in the study of the chemical combinations of atoms leading to the formation of molecule. However, it should be noted that octet rule is not valid for hydrogen and lithium atoms. This atom tends to have only two electrons in their valence shell, similar to that of helium 1s2, which called duplets. 5.2.1 Ionic bond. Formation of sodium chloride. Sodium chloride. The electronic configuration of sodium and fluorine are sodium Z equal to 11, 1s2, 2s2, 2p6, 3s1 or 281. Fluorine Z is equal to 17, 1s2, 2s2, 2p6, 3s2, 3p5 or 287. Internet, my friend. Search more atoms which complete their octet during chemical combination. Sodium has one electron in its valence shell. It has a tendency to lose one electron to acquire the configuration of the nearest noble gases, neon 28. Fluorine has 7 electrons in its valence shell. It has a tendency to gain one electron and thereby acquire the configuration of the nearest noble gas, argon 288. During the combinations of sodium and sodium atom transfers its valence electrons. to the chlorine atom. Sodium atom change into sodium plus ions, while the chlorine atom changes into chlorine ions. The two ions are held together by strong electrostatic force of attraction. The formation of ionic bond between sodium and chlorine can be shown as follows. Sodium reacts with chlorine to form sodium plus Cl minus. Sodium is 281, chlorine is 287. Sodium give one electron to chlorine and form into Na plus. And chlorine is formed into anion and valence shells in valence shell number of electron is 288. Na plus react with chlorine and form NaCl with the help of ionic bond or NaCl. Formation of calcium chloride CaCl2. The following representations show the formation of compound calcium chloride from the element calcium and chlorine. Electronic configuration of calcium 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Chlorine react with chloride. Two chlorides react with calcium to form CaCl2 or Ca2 plus Cl minus 2. 5.2 by 2. Ionic solids and lattice enthalpy. Ionic solids are solids which contain cations and are held together by ionic bonds. Constant treatment helps us to understand the formation of ionic bonds between ions of different elements. Formation of ions depend on the ease with which an atom can lose or gain electrons. Every in gaseous state form into M plus electron. X react with electron to give X minus and form electrogain enthalpy. M plus react with X minus to give Mx in gaseous form for Mx solid. 0. Cesium fluoride is the most ionic compound because cesium is most electropositive. Fluorine is most electronegative element. The electronegativity difference between them is the largest. Hence, ions are easily separable. The bond is weakest and the compound is least stable. Ionic compound ionization is always an endothermic process, where electron gain process can be exothermic or endothermic based on the ionization enthalpy delta IH. An electron gain enthalpy can predict which element can form ionic compounds. Element having low ionization enthalpy can readily form ionic bond with element having a high negative value of electron gain enthalpy. Both these processes takes place in gaseous phase. All ionic compounds in the solid states have each cation surrounded by specific number of anion and vice versa. Sodium chloride crystal lattice. The arrangement of cation and anion in a crystalline solid is ordered and they are held together by Coulombic force of attraction during their formation. This compound crystallizes from gaseous state Mk in gaseous state form into MXS to the solid state. The structure in which the crystal depend upon the size of ion, their packing arrangement and other factors. The overall stability of ionic solid depend upon the interaction between all these ions and the energy released during the formation of crystal lattice. Let us consider the formation of sodium chloride ionic solid. Sodium gaseous state formed into Na plus gas electron delta IH is equal to 405.8 kJ per mole. Chlorine in gaseous state react with electron to give Cl minus gas. Delta EGH is equal to minus 348.7 kJ per mole. Sodium plus gas and chloride minus form into sodium chloride gas and release 147.7 kJ per mole. Conversion of sodium chloride gases into sodium chloride solids is associated with release of energy, which is -788 kJ per mole. This released energy is much more than the absorbed energy. The stability of an ionic compound can be estimated by knowing the amount of energy released during lattice formation and not just by energy associated with completion of octet around the ionic species in the gaseous state alone. Lattice enthalpy. Lattice enthalpy of an ionic solid is defined as energy required to complete separate 1 mole of solid. Ionic compound into gaseous component. Lattice enthalpy of sodium chloride is -788 kJ per mole, which means that 788 kJ of energy is required to separate 1 mole of sodium chloride into 1 of gaseous sodium plus gas and chlorine minus gas to an infinite distance. 5.1 Lattice enthalpy value of some ionic compounds. Compound lattice enthalpy kilojoule per mole. Lithium chloride have lattice enthalpy 853. Sodium chloride lattice enthalpy 788. Barium difluoride is 3020. Calcium dichloride is 2258. Aluminum trichloride is 5492. For saying anion and different cation. First, cation having higher charge have large lattice energy than compound having cation with lower charge. Aluminum trichloride greater than calcium dichloride greater than sodium chloride. Second, as size of cation decreases, lattice energy increase. Lithium fluoride greater than sodium fluoride greater than potassium fluoride. 5.2.3 Covalent bond. In 1919, Lewis suggested that there are atoms which attain inert gas configuration, that is 1s2 or ns2 np6 configuration, by sharing one or more electron pairs with similar or dissimilar atoms. Each atom contributes 1 electron to the shared electron pair and has equal claim on the shared electron pair. Langmuir called the Lewis electron pair bond or covalent bond. Thus, the concept of covalent bond is known as Lewis-Langmuir concept. A shared pair of electrons is represented as a dash and is responsible for holding the two atoms together. A covalent bond may be defined as follows. Attractive force which exists due to mutual sharing of electrons between the two atoms of similar electronegativity or having small difference in electronegativity is called a covalent bond. Formation of hydrogen molecule. The electronic configuration of hydrogen atom is 1s1. It needs one more electron to complete its valence shell when two hydrogen atoms approach each other at a certain internuclear distance. They share their valence electron. The shared pair of electrons belong equally to both the hydrogen atoms. The two atoms are said to be linked by a single covalent bond and a molecule of hydrogen is formed. Hydrogen, two hydrogen with free radical form H2 by sharing pair of electrons. Formation of chlorine. The Lewis-Langmuir theory can explain the formation of chlorine molecule Cl2. The chlorine atom with electronic configuration neon 3s2 3p5 is 1 electron short of argon configurations. The formation of chlorine molecule can be understood in terms of the sharing of a pair of electrons between the two chlorine atoms. Each chlorine atom contributes 1 electron to the shared pair. In the process, both the chlorine atoms attain the valence shell octet of the nearest noble gas, that is argon. chlorine 1, 2, 3, 4, 5, 6, 7. So each chlorine has 7 electrons, share 1 electron to form Cl2. The dot represent the electrons. Such structures are referred to as Lewis structure. The Lewis dot structure can be written for other molecules also in which the combining atom may be identical or different. Following are the important features of covalent bond. Each bond is formed as a result of sharing of electron pair between the two atoms. When a bond is formed, each combined atom contributes 1 electron to the shared pair. The combining atom attain the outer shell's noble gas configuration as a result of sharing of electron. Thus, water reacts with carbon tetrachloro. The formation of covalent bonds can be represented as hydrogen acquire duplet oxygen acquire octet H2O. All atoms acquire octet carbon tetrachloro. Third, formation of multiple bonds. When two atoms share 1 electron pair, they are said to be joined by a single covalent bond. When two combining atoms share two pairs of electrons, the covalent bond between them is called a double bond. For example, a double bond between two carbon atoms in ethylene molecule. When two combining atoms share 3 electron pair, a triple bond is formed as in the case of two nitrogen atoms in a nitrogen molecule. Some other example of multiple bond are carbon dioxide and C2H2. N triple bond N, O double bond C double bond O, H single bond C, C triple bond C, C single bond H. Multiple bonding. 5.2.3 Lewis structure. Lewis representation of simple molecule. Lewis dot structure show a picture of bonding in molecules and ion terms of their shared pairs of electrons and octet rules. Although such a picture does not explain completely the bonding and behavior of a molecule, it helps to understand the formation and property of molecule. Step 2. Write Lewis dot structure. Add the total number of valence electron of combining atom in the molecule. Second, write skeletal structures of the molecule to show the atoms and number of valence electron forming the single bond between the atoms. Third, add remaining electron pairs to complete the octet of each atom. Fourth, if octet is not complete, form multiple bond between the atoms such the octet of each atom is complete. Fifth, the anion add more electron for each negative charge. Sixth, in cation removes or subtract 1 electron from valence electron for each positive charge. 7. In polyatomic atoms and ions, the least electronegative atom is a center atom. For example, sulfur in the center atom in sulfur tetraoxide 2 minus. Nitrogen is the center atom in nitrogen trioxide minus. 8. After writing the number of electrons as shared pair forming single bond, the remaining electron pair are used either for multiple bond or remain as lone pair. Table 5.2 include Lewis representation of some molecule. Table 5.2 Lewis dot structure of some molecule or ions. Molecules or ion. H2 H bond H O2 oxygen double bond O. O3 is O double bond O plus O minus. NF3 CO3 2 minus. OC double bond O single bond O. HNO3 is ONOHO. Problem 5.1. Write Lewis structure of nitrile ion nitrogen dioxide minus solution. Step 1. Count the total number of valence electron of nitrogen atom, oxygen atom and 1 electron of additional negative charge. Nitrogen is 2s2, 2p3, oxygen is 2s2, 2p4. 5 plus 2 multiplied by 6 is plus 180 electrons. Step 2. The skeletal structure of nitrogen dioxide minus is written as ONO. Step 3. Draw a single bond that is one shared electron pair between the nitrogen and each oxygen atom, completing the octet on oxygen atom. This does not complete the octet of nitrogen, hence there is a multiple bond between nitrogen and one of the oxygen atom, a double bond. The remaining two electrons constitute a lone pair on nitrogen. Following our Lewis dot structure of nitrogen dioxide minus ONO minus O double bond O N single bond O and O N double bond O minus. Problem 5.2. Write the Lewis structure of carbon monoxide molecule. Solution. Step 1. Count number of electron, carbon and oxygen atom. Valence shell configuration of carbon and oxygen atoms are 2s2, 2p2 and 2s2, 2p4 respectively. The valence electron available are 4 plus 6 equal to 10. Step 2. The skeletal structure of carbon monoxide is written as C single bond O. Step 3. Draw a single bond, one shared electron pair between C and O and complete the octet on O. The remaining two electron is a lone pair on carbon. The octet on carbon is not complete, hence there is a multiple bond between C, carbon and O, oxygen, a triple bond between carbon and oxygen atom. This satisfies the octet rule for carbon and oxygen atom. C triple bond O. Each hydrogen atoms attain the configuration of helium and duplet of electrons. Formal charge. The Lewis dot diagram helps us to get a picture of bonding in a molecule which obey the octet rule. In case of polyatomic molecule, double bond or some triple bonds are present and can be represented by more than one Lewis structure. In the case of calcium trioxide 2 minus, we can have 3 dot diagram OCOO2 minus. Double bond can be represented between the carbon and any one of the three oxygen atoms. Formal charge can help us in assigning bond between several structures are possible. Formal charge is a charge assigned to an atom in a molecules. Assuming that all electrons are shared equally between atoms, regardless of their relative electronegativity. While determining the Lewis structures per molecule, the structure is chosen such that the formal charge is as close to zero as possible. Formal charge is assigned to an atom based on electron dot structure of the molecular ion. Example O3 NH4 plus nitrogen double bond carbon double bond O oxygen minus S double bond carbon double bond nitrogen and minus. Formal charge on an atom in a Lewis structure of a polyatomic species can be determined using the following expression. Formal charge on an atom in a Lewis structure is equal to total number of valence electron in free atom minus total number of non-bonding or lone pair of electron minus 1 by 2 is total number of bonding or shared electron. Or formal charge is valence electron minus non-bonding electron minus lone pair of electron minus bonding electron divided by 2. Structure having the lowest formal charge has the lowest energy. First, let us consider ozone molecule O3. Lewis structure of O3. O double bond O single bond O. Here three oxygen atoms are numbered as 1, 2, 3. The formal charge on central oxygen atom number 1 is equal to 6 minus 2 minus 1 by 2 multiplied by 6 is equal to plus 1. Formal charge on the end oxygen atom is marked as 2 is equal to 6 minus 4 minus 1 by 2 multiplied by 4 is equal to 0. Formal charge on the end oxygen atom marked as 3 equal to 6 minus 6 1 by 2 multiplied by 2 is equal to minus 1. Hence, O3 molecule can represent along with formal charge as follow: oxygen double bond oxygen plus single bond O minus. The lowest energy structure can be selected using formal charge from the number of possible Lewis structure for a given species. Second, let us take the example of carbon dioxide. Carbon dioxide can be represented by the following: O double bond, C carbon double bond, O triple bond, carbon single bond, O single bond, carbon triple bond, oxygen. Assigning the formal charge on the carbon atom and the two oxygen atom number 1 and 2. Structure A. Number of electrons 4 from carbon and 6 from each oxygen. So total number of electron 4 plus 6 equal to 16. Formal charge on carbon is equal to 4 minus 0 minus 1 by 2 multiplied by 8 equal to 0. Formal charge on O1 and O2 is equal to 6 minus 4 minus 1 by 2 multiplied by 4 equal to 0. In this structure, formal charge on all atoms is 0. Structure 4. Formal charge on carbon is equal to 4 minus 0 minus 1 by 2 multiplied by 8 equal to 0. Formal charge on oxygen minus 1 is 6 minus 2 minus 6 by 2 is equal to 4 minus 3 is equal to plus 1. Formal charge on O2 is equal to 6 minus 6 minus 2 by 2 is equal to minus 1. Structure C. Formal charge on carbon is equal to 4 minus 0 minus 1 by 2 multiplied by 8 equal to 0. Formal charge on first oxygen is 6 minus 6 minus 1, 2 by 2 is equal to minus 1. Formal charge on second oxygen is equal to 6 minus 2 minus 6 by 2 is equal to 4 minus 3 equal to plus 1. We find that in structure A, the formal charge on all atoms is O, while in structure B and C, formal charge on carbon is O, while oxygen having formal charge minus 1 or plus 1. So the possible structure with the lowest energy will be structure A. Use your brain. Which atom in NH4 plus will have a formal charge plus 1? Generally, the lowest energy structure has the smallest formal charge or atoms. 5.2.6 Limitation of Octet rules. First, Octet rule does not explain stability of some molecules. The Octet rule is based on the inert behavior of noble gases, which have their octet a complete, that is, have 8 electrons in their valence shells. It is very useful to explain the structure and stability of organic molecules. However, there are many molecules whose existence cannot be explained by the octet theory. The central atom in this molecule does not have 8 electrons in their valence shell, and yet they are stable. Example: barium dichloride, phosphor pentafluoride, etc. Such molecule can be categorized as having. Problem: find out the formal charge on sulfur, carbon, nitrogen. Sulfur double bond carbon double bond nitrogen minus. Sulfur single bond C triple bond N minus. Sulfur triple bond carbon single bond minus. Solution. Step 1. Write Lewis dot diagram for the structure. Sulfur double bond carbon double bond nitrogen. Sulfur single bond carbon triple bond nitrogen. Sulfur triple bond carbon single bond nitrogen. Step 2. Assign the formal charge. Formal equal to formal charge minus load pair of electron minus 1 by 2 is bonding electron. Structure A. Formal charge on sulfur equal to 6 minus 4 minus 1 by 2 is equal to 4 equal to 0. Formal charge on carbon is 4 minus 0 minus 1 by 2 multiplied by 8 equal to 0. Formal charge on nitrogen is 5 minus 4 minus 1 by 2 multiplied by 4. Structure B. Formal charge on sulfur is equal to 6 minus 6 minus 1 by 2 multiplied by 2 is equal to minus 1. Formal charge on carbon is equal to 4 minus 0 minus 1 by 2 multiplied by 8 is equal to 0. Formal charge on nitrogen is 5 minus 2 minus 1 by 2 is multiplied by 6 is 0. Structure C is formal charge on sulfur is equal to 6 minus 2 minus 1 by 2 multiplied by 6 is plus equal to plus 1. Formal charge on carbon is 4 minus 0. Structure C. Formal charge on sulfur is equal to 6 minus 2 minus 1 by 2 multiplied by 6 is equal to plus 1. Formal charge on carbon is 4 minus 0 minus 1 by 2 multiplied by 8 is equal to 0. Formal charge on nitrogen is equal to 5 minus 6 minus 1 by 2 multiplied by 2 is equal to minus 2. First, incomplete octet. Second, expanded octet. Third, odd electron. First, molecule with incomplete octet, barium trifluorides, beryllium dichloride, lithium chloride. In this covalent molecule, the central atoms, boron, beryllium and lithium, have less than 8 electrons in their valence shell but are stable. Lithium in lithium chloride has only 2 electrons. Beryllium in beryllium dichloride has 4 electrons, while boron in boron trifluoride has 6 electrons in the valence shell. Molecule with expanded octet. Molecule with expanded octet. Some molecules like sulfur hexafluoride, phosphor pentachloride, H2SO4 have more than 8 electrons around central atoms. SF6 12 electrons around sulfur. Phosphor pentachloride 10 electrons around phosphorus. H2SO4 12 electrons around sulfur. It must be remembered that sulfur also forms many compounds in which octet rule is obeyed. For example, sulfur dichloride, the sulfur atom has 8 electrons around it. Sulfur dichloride, 8 electrons around sulfur. Use your brain power. How many electrons will be around I in the compound? Add in IF7. Odd electron molecule. Some molecules like nitrogen oxide and nitrogen dioxide do not obey the octet rule. Both nitrogen and oxygen have odd number of electrons. Nitrogen double bond oxygen. Oxygen double bond nitrogen plus O minus. The observed shape and geometry of a molecule cannot be explained by the octet rule. Third, the octet rule fails to explain the difference in energy of molecule. Though all the covalent bonds are formed in an identical manner, that is by sharing a pair of electrons, the rule fails to explain the difference in reactiveness of different molecules. Use your brain power. Why is hydrogen stable even though it never satisfies the octet rules?